Good morning, students. This is Mr. Allen, your AP Calculus teacher. Today we're going to be looking at the next lesson, which is section 1.2, which is on estimating limits using the graphic method and numeric methods. So I'm going to go ahead and try to share my screen again. All right, so section 1.2. So today's lesson has the following goals. Students will be able to estimate using a numeric or graphical approach. You'll learn different ways that a limit can fail to exist. And then this third bullet point, I'm making this optional due to the restrictions this year with our schedule. But if you are a super strong student and you're really interested, I would encourage you to look at the formal definition of limit. Okay, so why limits? Well, the last lesson we looked at, section 1.1, we talked about the tangent line problem and the area under a curve problem. And I've kind of given you some limits here, and I'm going to have to explain this notation here a little bit. But so what we have here is we have a limit. That's what this says. The limit as delta x, whatever that is, that's a change in x as x goes to 0 of this function. Well, it turns out that this limit actually will calculate the slope of that tangent line. Now, we're not going to worry about that today, but why limits? Well, because to solve this problem, we need limits to actually do that problem. Similarly, the area under a curve problem, this limit, which it looks even more ugly, more complicated, but basically this limit, which involves a summation, gives you the answer to this problem, because it's basically taking these rectangles, which there's 8 of them here, and it's making the width of those rectangles go to 0. In other words, there would be infinitely many rectangles there to give you the exact area of that curve. So let's consider a very basic problem. Consider the function f of x equals x. And I've even got it graphed here for you. Clearly, this is not a problem. You could easily figure out what that function is. You're familiar with it. It's a line with a slope of 1 and a y-intercept of 0. So if I asked you, if I literally said, class, try that again. There we go. So let's say I wanted you to find the limit of that function, f of x as x goes to 2. Well, here's where x is equal to 2. So my question is, what would you guess the y value is when x is equal to 2? What would you guess? Well, I would hope you would guess that it's 2. So you would probably guess that that answer is 2. And you'd be exactly right. In fact, you could have done something called direct substitution. To evaluate this interval. In other words, you could have just done f of 2. F of 2 is 2. Now, the reason I'm showing you this is because I think that calculus, sometimes we focus on the really hard examples and don't take time for the easy ones. And then when the student gets an easy one, they just totally botch it up and make a mistake. If a function is a nice continuous function, finding limits is trivial. You basically just plug the value of x in and get the answer out. It's not very interesting, so we don't spend much time talking about that. In fact, if I asked you to find the limit, and this is the notation we use, the limit of f of x as x goes to question mark, so you could put in whatever number there you wanted. I'll put in negative 5.2. Guess what the limit of f of x as x goes to negative 5.2 is? Well, you would plug negative 5.2 into our function here, and you'll get negative 5.2. Okay, moving on. Let's consider a more interesting function. Let's consider the function g of x. Now, I'm going to use my graphic calculator here a little bit, and you can play around with it too if you want to plug that into your graphic calculator and graph it. Now, this is the graphic calculator that I would recommend that you use for this class. It's a TI-84. And what we're going to do is we're going to try to estimate this limit using the graphic, and we're going to use the numeric methods. Okay, so I'm going to go ahead and go to the next slide. And if you plugged this function into your calculator and then you looked at the table, this is the numeric solution. Numeric means number. So it means look at numbers to estimate. So, oh, and I guess I should emphasize this again. A limit, this is an intuitive definition. A limit is an, let's say this correctly. A limit is just a predicted, that's a good way to say it. It's just a predicted y value. So in other words, what I'm asking you to do here, I guess I wasn't super clear here. I said near 1. I'm asking you, what is the limit as x goes to 1 of this function g of x? Let's say we're trying to figure out what that is. So we can look at our table to find it numerically, to guesstimate it. And remember, a limit is a predicted y value. So as x gets closer to 1, now what I'd like you to notice is, what is the value of the function at x equals 1? Well, it says error. It's not really an error. The calculator can't do it. It doesn't exist. And the reason it doesn't exist is this function, when you plug 1 into it, you're dividing by 0, which we know is not allowed. However, what do all of these values and those values, as we get closer and closer to that magical 1 value of x, what do they seem to be approaching? Well, I'm hoping that you can see that it's getting closer and closer to the magic number -1. So I would guess that the limit as x goes to 1 of g of x is equal to -1. Now, I need to make sure that this is clear. Remember, this is a predicted y value. I'm not saying that g of 1 is -1. That is not a true statement. We can clearly see that that's not the case based on this calculator. What we can say, though, is the limit, as we get super close to 1, without actually getting there, it is -1. So that's what a limit is. So this was the numeric method. Here's a graphical solution. This is probably the easiest way to do it. If you were to graph this function, by the way, this is g of x. And remember, g of x was, I think it was x squared plus, oops, actually I think it was minus 3x plus 2 over x minus 1. If you were to graph this in your graphing calculator, and I think this is going from -10 to 10, it'll look linear. And I'll explain more in our next lesson why that is. But if you zoom in, you will actually see, looky there, there is what we call a hole, which you probably remember from pre-calculus. So this is a removable discontinuity. We have a hole. This is actually when x is equal to 1. But guess what this y value is right here? Guess what that y value is? I'm going to go back one. Guess what that y value is right there? We're trying to look. We're trying to guess. I think it's negative. I think it's -3, or I'm sorry, it's -1, right? Isn't that what we said on the last one? Yeah, it's -1. So it's going to be -1. So again, you can use a graph to do that. So that here again, the limit is -1. So in example 1, we'll note that the function is undefined when x is equal to 1, yet g appears to be approaching some limit as x approaches 1. And remember, that limit turned out to be -1. Remember, that's the y value, not the x value. This often happens, and is important to realize that the instant existence or non-existence of f of x at c has no bearing on the existence. Now here I'm talking about f of x because I'm talking about a general function. This is very important. What I'm telling you is this: the function doesn't have to be defined at some x equals c. However, the limit can be defined there, and that's why we need it. So let me say that again. The existence or non-existence of f of x at c has no bearing on the existence of the limit as x approaches c. Okay? If you go back to that example I did initially where I said that f of x was equal to x, well, at x equals 2, the function existed there, and its output was 2. But on the second example, when we did g of x, g of 1 did not exist, but it did have a limit there. Okay, so then the other pieces that we need to do today, and we're getting close to 10 minutes, so I'm going to speed this up a little bit, there are three common types of behaviors associated with the non-existence of a limit. In other words, when a limit is going to be called D and E is the term I'm going to use in this class. The first one is when it approaches a different value from the right side than it does on the left. Number two is when it increases or decreases without bound. In other words, it goes to infinity or negative infinity. Then when it oscillates, now I'm only going to do an example of one. If you're interested, this one here is actually pretty cool. Consider this limit, and I think I'm getting this right, but it's the sine function with 1 over x. We may do that in class, but this is a great example of, this limit here is D and E. Does not exist, and the reason is because it's oscillating between two fixed values. But anyways, let's do an example of the first type. So we want to show that the limit as x goes to 0, the absolute value of x over x does not exist. Now, as you can see, this function here is a little bit more complicated than the easy ones I did in the first couple of examples, but we're going to break it down into something a little bit more simple. So this function, we'll call it f of x, absolute value of x over x. Well, first of all, let's talk about what our definition of absolute value is, and you may or may not know that, so I'm explaining it to you now. It turns out that the absolute value of x, if you think about the graph of that function, it would look like this. You have your x and your y-axis, and it's that V shape, right? Well, what's the equation of this line or ray over here? Well, that's x. So when x is greater than 0, we'll use the x function. Over here, what's the slope of this? Well, that's negative 1, right? So that's negative x when x is less than 0. So this is the definition of the absolute value of x. But we're not just doing the absolute value of x, we're doing the absolute value of x over x. Well, if you take x over x, you get 1, correct? If you take negative x over x, you get negative 1. So we've just defined what the absolute value of x is. So furthermore, we can define this function using this piecewise defined function. The graph of this curve, and it's not really a curve, is this right here. It goes this way here, it goes this way here. You've got an open circle here, and you have an open circle there. Now, clearly, I hope, if I asked you about the limit as x goes to 0 of f of x, we have a problem. And the problem is this. If I'm coming up here from this direction, what y value would you guess I'm going to as x goes to 0? Well, I think you'd guess 1. But if I look down here, and if I'm coming in from the left, you probably guess that y is going to negative 1. So 1 does not equal negative 1. Therefore, this limit is D in E. It does not exist. This is our first example of a limit that doesn't exist because the f of x approaches a different value on the left than it does the right. Okay, on the right it's approaching 1, on the left it's approaching negative 1. Those are different, therefore it doesn't have a limit. So limits does not exist. We'll call it D and E. Again, this is how you would write that. So I would like the limit as x goes to 0 of the absolute value of x over x equals D and E. It doesn't exist. Again, here are those three possibilities. Now, this last piece here as we end our lesson, I'm not going to spend any time on, but it's the formal definition of limit. It is pretty technical. If we have time somewhere along the way, maybe we can talk about it. I don't think we're going to have time. It's pretty challenging. This is the definition. I'll let you look at that, but we're getting close to 15 minutes, which is longer than I like these videos to go. So I'm going to go ahead and call it a day. And that is section 1.2.